I just want to say John has been such a great advocate and partner in this. He's also the thrust leader and is one of the first people I talked to as the Institute was forming. So thank you, John, in advance, and I'll pass it over to you.
Thank you, Scarlett. Good afternoon, everyone, and thanks so much to the Cocoziello Institute for the seed grant funding in support of our research on lying glass for architectural applications. So what is the problem that we are trying to solve? If you look around, all modern architecture has windows. It has lots of windows. And window composition has not changed in a very long time. In fact, the global glass industry produces about 86 million tons of carbon dioxide each year. Now, standard window glass is called soda lime silicate glass. Soda after the soda ash, which is sodium carbonate, lime after limestone, which is calcium carbonate, and silicate after the silica sand. Now, when these are mixed and melted together, the carbonates release carbon dioxide into the atmosphere as they decompose into oxides. Soda lime silicate accounts for more than 90% of the global volume of glass being manufactured. So if we want to do something about this, we need to do something that makes a step change away from soda lime silicate, and the biggest market for that is in architecture. So Lion Glass is Penn State's patent-pending family of glass compositions named after our Nittany Lion mascot. Lion Glass reduces the carbon footprint of the glass industry two ways. First of all, it eliminates the use of carbonate batch materials, so that part of the carbon footprint is completely gone. Secondly, it dramatically lowers the melting temperature of the glass compared to soda lime by about 400 degrees C lower compared to soda lime manufacturing. This table shows the milligrams of carbon dioxide that are released per gram of glass that is being melted. You can see that nearly 20% of the soda lime batch gets released into the atmosphere as carbon dioxide, whereas with Lion Glass, since it eliminates the use of carbonate batch materials, that part of the carbon footprint is eliminated. We are delighted by the excitement around Lion Glass. It's been featured in BBC World News. It was highlighted in a Big Ten Network Impact segment that you got to see during all the Penn State football games. And because of the generous internal support from the university, from the Cocoziello Institute, and from the Office of the Senior Vice President of Research, we're able to file for 3 different patent applications to cover the compositional family and the uses of Lion Glass without any strings attached to external sponsors. We've got an awesome team here on this architectural project. My partner in crime here is Professor Julian Wong, who is an associate professor of architectural engineering. So I'm bringing the material science expertise. He's bringing the architectural engineering expertise. We've got a great group of postdocs and students, and the one who's leading the charge on this is Mehmet Oze, who's sitting right there. He's also responsible for putting together this great presentation. So thank you, Mehmet. Now, if we look at the different components of a building, we can evaluate their energy efficiency in terms of this U coefficient, which is a heat transfer coefficient. This tells you how much heat is lost per unit area. You can see something like a roof or an external wall has a very low U value, so it is good for thermal insulation. The worst part of a building is typically the windows, I'm ashamed to say. For a standard single pane window, the U value is about 2 watts per meter squared Kelvin. So we need to do better. And the way to do better is, first of all, through the design of the insulated glass unit or insulated glazing unit, through use of double pane windows and other IGU technologies. But any Lion Glass that needs to be used needs to show that it can not only reduce the carbon footprint of the glass manufacturing, but also at least meet the same standards that are met for energy efficiency of buildings used with soda lime. So the goal of our seed grant project is, can we produce sheets of Lion Glass? Can we coat Lion Glass with low E coatings, such as used in architectural applications? And can we develop a prototype IGU using sheets of Lion Glass? So Mehmet and team have been on the case. They've gone through lots of steps here to be able to make really nice quality pieces of Lion Glass, the largest pieces that have been made to date. There was some troubleshooting along the way, and Mehmet figured it out. You can see here he is pouring this heavy crucible of Lion Glass on the left. In the middle movie, you'll be able to see the Lion Glass after it's been poured. It's glowing, but the glow is a lot less compared to soda lime because the temperatures are so much lower. And there's a beautiful piece of glass that he is using together with Julian Wong for testing the properties that are needed for architectural applications. So low E coatings are an essential part of architectural glazing. One of the goals of windows is to allow for as much visible transmission of light as possible while reflecting as much of the infrared and UV parts of the spectrum as we can to ensure that there's good thermal insulating behavior between the inside and the outside while allowing for good visibility. And so one of the technologies that is used is a low E coating. This is on the order of a couple tens of nanometers. Very thin layers of silver and or titanium and titania are used. And Mehmet was able to show, this is an uncoated lying glass here. You can see how beautifully clear it is. And then the coated lying glass just to the right of that. And the emissivity values are shown in the table on the lower right. You can see the uncoated soda lime silicate with a higher emissivity, about the same as lying glass, and then the coated range right below that. So coated soda lime silicate at an industrial scale goes between 0.01 and 0.15. And already, even with this first lab sample, which is not the quality that one would expect in industry, it's still falling within that range of soda lime. Optically, it is also looking great. On the left, you see the percent transmittance of lying glass versus soda lime. The uncoated lying glass is shown in black. You can see the excellent transmission across the spectrum. One of the other nice features of lying glass is that it does not have that same greenish tint that standard soda lime silicate glass. Like if you take a window and you look at it through the width rather than through the thickness, you'll notice it's not actually clear. It's green, and it's green because of iron contamination in the soda ash and in the limestone. First of all, we're getting away from those bash materials, but also lying glass can tolerate a greater amount of contamination from iron before it actually shows any visible coloration. So it's actually clearer compared to soda lime, and you can compare then the transmission spectrum of the coated lying glass sample in red versus the coated soda lime sample in blue. And if we look on the left there, this shows the percent of the reflectance, and across the visible or the infrared spectrum, we're getting really good reflectance, which is what we want in order to have good energy efficiency. So I thank you very much for your time. Thanks to Mehmet for all his excellent work, both in the research and putting this presentation together. And are we taking questions now? We are taking questions now. I'm happy to address any questions. Thanks, everyone.
So what's the rate limiting step? Why can't we get this moving faster?
Thank you for asking that question. Thank you for asking that question several months ago and giving us the support we needed to increase our number of furnaces, which are on their way. They're going to start to be delivered within the next few weeks to the next month. So we are in the process of basically doubling our furnace capacity. Then what becomes the rate limiting step? Then I would say the rate limiting step is going to be resolving whatever scale-up issues need to be resolved with our industrial partners. In the architectural space, our main partner, I guess I can say this now. So we're about to have a contract with Vitro, which is a float glass manufacturer whose U.S. facilities are based in Pittsburgh. We're really excited about this because I think it's consistent with our mission as a land-grant institution that we're able to partner not only with a domestic manufacturer, but one that is based almost in our backyard here. And what makes it extra special for me too is that the PhD student who's coming to work on this is actually a Penn State graduate who worked with my predecessor, Dr. Carlo Pantano, who was also the director of the Materials Research Institute for many years. He got his bachelor's and master's degree with Carlo. I was actually part of hiring him up at Corning. He left Corning to go to Vitro. I left Corning to come here. And now he's coming back to do his PhD on exactly this project, and I'm just really excited about this on multiple levels. Thank you. Other questions? Yes.
Thank you so much for your fascinating project. I wonder how the U value and the thermal resistance of the new window compares with the double pane or three pane windows.
Great question. My expectation is that the performance should be very similar to the performance with soda lime silicate. And the reason is that the thermal conductivity of glass really doesn't change all that much from glass to glass. The reason is because of the non-crystalline structure of glass. So, materials that have really good thermal conductivity are things like diamond or other perfect crystals that are able to propagate the waves without having any scattering. With a glassy material, it gets scattered like every step of the way. So we should have very consistent performance, and our peak in the box here with coatings indicates that lime glass should work just as well with coatings compared to soda lime. So I think the overall performance is going to be similar. One of the main differentiators may be the lack of the greenish tint, which I think is a higher end window and also higher end glass packaging too, if customers request that.
Thank you so much.
Yeah, thank you. Yes.
So I'm wondering about some of the aspirations for this glass. For instance, there was a slide that said it's maybe 10 times stronger. Does that help us maybe in windstorm protection and things like that? Is that one of the aspirations? And then my second part of the question is, we've built buildings with curtain walls of glass that use structural glass beams, and it's because it has so much compressive strength and also, the resistance for breakage. How does Lion glass fit into that for other architectural uses?
Great question. Yeah, this was one of the surprising features that we found in Lion glass, that it has about 10 times the damage resistance compared to soda lime. This is as measured by how much force is required to initiate a crack. So with a brittle material like glass, failure happens in 2 steps. The first step is the introduction of the damage, and then the second step is once the damage is introduced, how much more additional stress is required to failure. With Lion glass, what we're doing is improving that first step. We're improving the resistance to damage. So if this is used in an application where there may be a sandstorm or there might be hail, it can help prevent the introduction of damage in the first place. This also might make it suitable for, say, photovoltaic substrate applications. So yes, I think it is a key part of the value proposition for Lion glass, and not just for architecture, but also for glass bottle applications. There's additional value to going to lighter weight bottles, because that requires less raw materials to melt, less energy, less transportation cost and transportation energy. So yeah, we're hoping that we can leverage that in the architecture space.
Many fronts you can
Yeah.
go after.
Yeah.
And how about your 3 patents that you're chasing right now?
Yes. Our 3 patents. So the first patent covers the first kind of broad compositional space and articles made using those compositions. During our research, we found a better compositional space that had improved properties, better manufacturability. So the second patent covers that compositional space, and the third one covers some specifics related to flat glass.
Nice.
Yeah.
Thank you.
Great. Thank you.